I don't know if you want to maybe just introduce what you're about to speak about while we're getting Ariel set up.
Yeah, happy to say a few words. So, what we'd like to kind of present is some new research that we've been working on over the past 2 to 3 months, something called Plookup. I think it might have been Kev who coined the original name. Essentially, what this is it's a scheme that implements efficient lookup tables via polynomial commitments, and the idea is that it can be integrated quite easily into a snarks proving system that uses polynomial commitment schemes like PLONK. What it does is the goal of it is basically to make snark unfriendly algorithms a bit more friendly by replacing computation with lookups, because computation is hard, and why bother doing work when you can just refer to someone else's computation instead. So the idea is to basically implement key value mappings over pre-computed tables that can be used to create extremely efficient circuits. So, for example, things like exclusive OR operations on binary like values, doing things like 16-bit range checks, and even things like looking up elliptic curve points from a pre-computed table for Pedersen hashes. These operations become extremely efficient because the lookup is effectively constant complexity. It just adds one gate into the circuit. So it can increase the efficiency of proving systems like PLONK by literally over an order of magnitude.
As we know, snarks are easy prey in a world of nasty binary function. What that means is that, for example, say we have 3 field elements, and we want to show that the third is the bitwise XOR of the first 2 when thinking of their binary decomposition, when thinking of them as 8-bit strings. So the way we're used to doing this in snarks is basically we explicitly write the binary decomposition of A, B, and C, and then prove that bitwise prove these binary decompositions are correct, and then prove that the bitwise XOR holds for each bit. So basically, this would take you 25 to 32 constraints, say in R1CS. The difference between 25 and 32 is if you insist on also checking the binary decomposition of C or just inferring it. Right, so the basic problem at a high level is that we need to represent our operations in native field operations. So we have, and okay, 25, 32 is not a big number, are not big numbers, but the reason it's painful is this is a multiplicative factor we pay, basically. Say we write SHA-256 as a sequence of 8-bit operations, right? We have the rotates, the bitwise ands, the bitwise XORs. So each such operation, we're going to pay this this multiplicative factor. And one approach for this problem that has gotten a lot of attention in the last few years is to not let our snarks out into the cruel world of arbitrary bitwise operations, but rather keep them in friendly neighborhoods of new hash functions that are being designed that are based solely or almost solely. I confess I'm not a big expert on these new functions, but basically that consist of native field operations like cubing, square roots, inverses. And this approach is getting a lot of attention and has a lot of, has advantages. Right. So maybe to answer Dara's question, I guess I was thinking it's 25 because it's like 16 for the binary decompositions of A and B, then another 8 for the bitwise XORs, and I was thinking there's another one there for checking, I guess for checking that these are really the binary decompositions. I didn't count it carefully. Maybe you can do 24. Dara's more of an expert than me on this. So basically, an alternative approach to this that was used in the ARIA system, for example, is let's do something else. Let's not explicitly represent the logic of these bitwise non-native operations. Let's, for example, just pre-compute a table of all the legal input-output tuples. So let's pre-compute a table of all A, B, and C in the field, such that if you look at their binary decomposition, all three of them will be 8-bit strings, and C will be really the XOR of A and B. Right, so the idea here is instead of trying, working hard to represent efficiently the logic of this non-native operation, let's just try to somehow check that this tuple ABC is in our pre-computed table. And the point is that if you do enough lookups, then there's going to be some cost for this table and enabling this operation of checking that things are in the table. But if you do enough lookups, this is going to be have an amortized cost of sort of one constraint per such operation. All right, so how does this protocol of proving that values are in the table work? So a slightly awkward but also nice thing that happened was that while preparing the slides, we actually came up with a protocol that's simpler than the one in the paper. It still doesn't be, when you really count the constants, it seems to be not as good as the one in the paper, but for explaining how to do such a thing, it's much cleaner and simpler. So that's what I'm going to try to show you now. Yeah. So the basic tool here is a multiset check. So we're given two set or multi-sets of values. There can be repetitions. And we want to check that the A's and B's are equal as multisets. So they contain the same elements, even counting repetitions, but maybe in different order. So this is a basic tool. And here's how you can do it. So you choose some random gamma in your field. So think the A's and B's, even if they're different, it could be that if we take the product of all the B's and all the A's, we'll get the same thing, right? Say the A's are all ones and the B's are half 1 and 2. So we can't just compare the product of the A's and B's. But say we after you've fixed the A's and B's, we choose some random gamma. And now we compare, again, the product, but where everything is shifted by this random gamma. So obviously, right, if the A's and B's are the same, just maybe not in the same order, then these products will be the same. And what you can show from the Schwarz-Zippel lemma pretty easily is that if they're not the same, then with very high probability over gamma, the product will be different. So right, with the simple randomization, we've reduced this multi-set check to just one product check. And so a big part of PLONK is saying that, okay, how am I given these A's and B's? So if I'm giving the A's and B's as like values of polynomials that I have commitments to, then there is a extremely efficient grand product protocol that then enables you, just given sort of the commitments to the A's and the B's, to do this check. All right, so we have this basic tool, the multi-set check. And now another small element. So now let's say the witness is these values fi, and the table is these values ti's. So we want to prove that the f's, now not as multi-sets, just as sort of sets, the f, all the values in the f's are contained in T. So one thing that may confuse you, right? We had tuples before, and now we just have these single elements, both in the witness and the table. But it's sort of an easy exercise that with randomness, you can reduce from the tuple case to this single element case. Okay, so here's how the simplified protocol we came up with 2 days ago works, and I'll give it just on a specific example. So say our witness is the multiset 311, and our table is 134. So right, so the claim is true. All the values of f appear in T. And now a prover wants to convince you of this. You have just a commitment to f, polynomial commitment to f. So here's what you do. The prover will commit to a sorted version of f union T. Here, I hope it's not confusing. I'm sort of shifting between talking about sets and multisets, but here I mean sort of a union as a multiset, as even an ordered, I guess, multiset. So right, so S is the vector 1, 1, 1, 3, 3, 4, right? If you take all the values in F, all the values in T, you take their multiset union, you write them, you sort them. This is the S you're going to get. All right, and now the prover is going to show that. So the prover commits, sends this commitment to S, and now using this multiset check protocol, the prover is going to show that as multisets, S and F union T are the same. And a minor technical point is that using sort of the PLONK grand product, if you have commitments to F and T, then doing the grand product over F union T is not a big deal. All right, so right at this stage, we know that S is equal. At this stage, we know that S is equal to the union of F and T. But that doesn't. It could be still at this point that there are things in F, and it shows so far that whatever is in F is either whatever is in S is either in F or T. But still, at this point, there could be things in F that are not in T. At this point, we don't know that yet. Otherwise, right? So now what we'll do is we'll look at the difference multiset of S. Call that S prime. What do I mean by difference multiset? Very simple, right? We look at the elements of S, and we just take the difference of each two adjacent elements. So right, we're going to get a vector or a multiset of size 1 less than S. Just and right, we're just going to you just do the computation. 1 minus 1, 0, again 0, then 2, 0, 1. Right, basically every time there's a repetition, it's going to give us a 0. Right, the repetitions here are what makes it sort of non-trivial. If F was allowed to use just each value of T just once, then we could just do a divisibility check between sort of the polynomial whose roots are F and whose roots are T. But the multiplicities here are the potential problem, that maybe F uses something from T many times, like is happening here with 1. Right, so this is the difference multiset. You're basically going to get a 0 for each repetition. Cool. And also we'll compute this difference multiset of T. So call it T prime. So right, it's 3 minus 1. We're going to get 2. 4 minus 3, we have 1. So we have this S prime and T prime. And now what we're going to show is basically that the non-zero differences in S prime are exactly the non-zero differences in, or the non-zero differences in S are exactly the non-zero differences of T. And why can we do this at this point with just a multiset check? Because we already know that S is F union T. And we know that, we know that the differences coming from F and not from T, from the repetitions, in a sense, are just going to contribute zeros. How many zeros? Like the size of F. So basically, the prover checks that S prime is T prime union as many zeros as the size of F. So this is the simplified protocol. So I think I'll give you maybe a minute to process it and see if there are questions, and if not, I'll hand over to Zac.
Actually, even while while people are thinking about questions, I'm wondering if Zac could potentially continue, only because we're currently running a little bit overtime into the break. And yeah, although I get it, I think, Ariel, you want to keep that slide up in a way, right? Oh, can you hear me?
I turned on my volume now.
Okay. So yeah, I think you want people to continue to be able to see that slide, right?
Yeah, but I think, yeah.
I wonder how we could do this. I might actually, if I bounce out, I wonder if, Zac, you could share your screen in my place.
Yeah, happy to try that. Yeah.
Because then you could actually keep Although actually then I'm not
I
there.
mean,
So
that might distract from Zach's presentation, so I'll stop sharing and I'll put it back on after Zach's talk for the Q&A, maybe.
okay, cool. What I'm gonna do, just so you know, is in the next, like right now, we are kind of going into our break time. So I will probably actually jump out of here to get the next speaker ready, and you can continue. You should keep going as long as there are people in this session and that people want to continue to be part of it. So why don't you set up your slides, Zach, and I'll make them big, and then I'll bounce out. I can also bounce back in. Just to
Sounds good. Okie dokie. So sharing screen, F5. Right.
nice.
All good?
Looks good. There you go.
Cool. So yeah, so this is a kind of a follow-on mini talk from Ariel, just going over what you can do with these lookup tables and the kind of the implications for common algorithms and circuits, and what are the trade-offs, what are the costs. And so working title for Plookup with PLONK is something we're working on called UltraPlonk. Still very much an active work in progress. With plookup, what it enables is extremely efficient key value mappings, because those witnesses F that you're proving are members of this multiset T. F can in UltraPlonk will be kind of a random linear combination of multiple witnesses. So, for example, if you want to do an exclusive OR operation, you can take your two operands, create a random linear combination of those and the claimed output of your exclusive OR table, and that becomes an element of F. And you can do a similar thing to construct the elements of T from pre-computed polynomials. You can also create a simplified version of the lookup table, which is in our paper, for scenarios where you don't need, basically for range proofs. If you just want to prove that something is within a range, you can do that very efficiently up to about ranges of like 2 to the 16 are extremely practical. Once you start getting above that, the size of the lookup table is going to get quite large, which does have a knock-on effect on your the previous computations. So yeah, the pros of it is you literally get over an order of magnitude efficiency increases relative to R1CS for common algorithms, things like conventional hash algorithms, Pedersen hashes, range constraints. So I just realized I didn't actually, sorry, I'm supposed to add, add a reference there. But so you can implement the RAM construction of some the tiny RAM architecture very efficiently. So you can do things like kind of access a RAM element in a tiny RAM-like construction in a single gate instead of having to have a logarithmic factor for accessing your memory. And you can implement niche number systems via these lookups. And by niche here, I am absolutely referring to things like the integers in the world of snarks. Like anything that is just like kind of not your native prime field modulus is difficult to work with. But you can do things like not just integers, but also obviously prime fields that aren't the native circuit prime field. And even things like binary fields within a prime field-based snark for things like if you want to do AES encryption. The downsides are it does add extra previous commitments. In the paper, it's 3, but we're fairly confident we can get that down to 2 once integrated into PLONK. The table size can add proof of work. You might need to add dummy gates into your circuit if your table size is significantly larger than the number of actual constraints in your circuit, which does limit the size of these tables, particularly if you're doing things like creating small circuits to be for proofs that are designed to be constructed in a web browser. It's tricky to integrate into sparse snarks, like the constructions that Justin was describing earlier. I'm sure it's not insurmountable, but one of the irritating problems is you need to, for this kind of sorted list, where you're computing a set of the differences in your sorted list, you do need to kind of access adjacent elements in your list. And so if your list is sparse and is full of zeros, that's more difficult to do. And also there's a proof of concept implementation of plookup written by Kev at Dusk Network, just linked to it below if anybody wants to have a gander. So yeah, UltraPlonk is an iterative upgrade from TurboPlonk, where TurboPlonk was basically Plonk with custom gates, custom constraints to do things like Pedersen hashes and binary arithmetic. And this is and so effectively a lot of the infrastructure that we developed for TurboPlonk can kind of be replaced by these lookup tables. And the overall effect on kind of the proof size and the number of amount of proof of work, it's relatively small. So UltraPlonk has gone down up to 13 n G1 scalar multiplications, where n is the number of gates in your circuit. The original Plonk was 9, but you can gain the number of actual gates in your circuit gets reduced by between a factor of 2 and 100, depending on the algorithm you're executing. And the proof length is very small. It's still it's well under a kilobyte. My final slide is basically just some gate counts. How many gates does it actually take to do common algorithms if we use UltraPlonk? I've got 2 numbers here. One is if you're kind of the tables that you're using have 2 to the 12 elements, and 1 for 2 to the 16. So the 2 to the 12 context is if you've got a circuit where the number of gates is about 2 to the 16. You don't want a lot of like lookup tables who themselves are the size of your circuit, because this commitment to S, this sorted list, kind of requires at least as many entries as you have in your lookup tables. So that can become very costly if the lookup tables have a similar size to your circuit size. But you can see here, basically, compared to TurboPlonk, compared to R1CS, the lookup stuff, it's a profound change in basically what's possible with pairing-based snarks now. Things like hashes become like almost like approximately 10 times or 20 if you're doing Pedersen times more efficient. You can do an entire 512-bit Pedersen hash in 64 constraints, and you can even start to do things like prime field multiplications over like arbitrary prime fields extremely efficiently. So this number I've given here for these prime field moles, that's assuming I should have added a bit more context here. That's for like a 256-bit prime field whose modulus is not equal to your native circuit modulus. With UltraPlonk, with range lookups, it's about 32 constraints, which means that things like recursive snark compositions, without having to rely on cycles of pairing-friendly curves, becomes extremely practical. This is all still a work in progress. We're still implementing this, but we're very confident that we can get the number of constraints to verify a recursive snark down to about 200,000, which that's like 2 to 3 seconds of previous time. We're very, very hopeful. This will make a lot of snark unfriendly algorithms much more feasible to implement. That's about all I had to share. Hang on.
There's a question here. There's a couple questions, and actually people should feel free to add questions in here and vote on the questions that are already in there. I don't know if you would like to take one of them. Do you see the ask a question at the bottom?
Yes, I do. Why does the non-native field multiplication cost grow with increasing services? That's because I made an error and I put those in the wrong order. It should shrink. My bad. Are Pedersen hashes cheaper than Poseidon and UltraPlonk? I think they will be. They'll become quite similar. I'm not sure. So my knowledge of Poseidon, it's a little old. I can't remember if Poseidon can benefit much from pre-computed tables. If it can, then Poseidon will have a similar increase in efficiency. Can't recall off the top of my head. They should be at least more similar than they currently are in our CS based constructions.
I would guess yes. I would guess that it would be cheaper.
What kind of recursive proofs are we going to implement using plookup? Well, one of the advantages of basically just brute forcing recursion is that the verify runtime is constant, depending on your it's not a function of your circuit size, which means you can verify arbitrary circuits with arbitrary verification keys for the same cost, like with no additional complexity. So what we're looking to do with it in the immediate term is implement zkSummit rollup on Ethereum, so that you can do basically. Last November, we launched our Aztec. This January we launched the Aztec protocol on Ethereum for private payments, and we want to. Our first plan is basically to add full anonymity into that construction, and also reduce the gas costs by well over an order of magnitude by using a zkSummit rollup construction. We have a rollup that aggregates private transaction snark proofs, but the ramifications are much wider than that. You can start to do things like, theoretically, if the implementations can get refined enough, implement light clients as smart contracts inside Ethereum. So you could do things like implement a Bitcoin light client via snark circuit, for recursive snark circuits, so that you can have basically a trustless oracle on Ethereum for the state of Bitcoin. And yeah, you can also, something we're exploring is creating multi-party computation constructions using recursive snarks. The kind of the scope of what you can do is now increased significantly. Yeah, I hope that answered it. Justin, it's definitely more of a manual process right now. What we're doing right now is our PLONK pre-verify libraries. It's called Beresenberg. It's all open source, and right now what we're doing is implementing gadgets on it, which explicitly kind of call these lookup tables. I haven't really making a transpiler that takes a binary circuit and figuring out the lookup tables. It seems non-trivial.
Yeah, I think that. Can you hear me?
Yep.
So I mean, yeah, maybe to state the obvious. I mean, the good thing is for like the common things like SHA. It's very natural and obvious what you'll do a lookup table for. You'll do a lookup table basically for the bitwise XORs and bitwise ANDs, and that pretty much gives you like the speed up.
Do you want to answer another one of the questions here?
Yeah, Dev, I wondered, could you expand a bit on your question? Like what kind of yeah, I'm not sorry. I'm not.
Actually,
what kind of structured operations do you have in mind?
if Dev is here and if you're available, we could actually bring you onto the screen. I don't know if that would be something interesting. Dev, are you around? Let's see if he's hearing us. Waiting for him in the chat. Okay, I'm going to bring him on.
Oh, I see what you're saying. So it's basically if the two operands are kind of commutative. We haven't really explored that, to be honest. Yeah, there might be, but it's not something that. Hey, Dev.
Can you hear me?
Yeah.
Yes.
I can no longer hear.
Can you hear us now? Nope, he's muted. Okay.
I mean, I think, well, maybe while he, yeah, it seems like an interesting idea if we can use the commutativity of bitwise XOR to get the table down by half. I didn't think about it. It's an interesting thing to think about.
Yeah, you probably yeah, if you're willing to represent integers in a bit of a freaky way by using multiplicative subgroups. So you have like roots of unity over a subgroup whose size is like 2 to the 8. Then you might be able to. Yeah, something really worth exploring. It's not something. I don't think something Ariel and I've really spent a huge amount of time thinking about.
Yeah, I mean, what one thing to say is this, right? This thing I mentioned about compressing tuples to like ABC to a single thing. That usually you do it with some random combination that ruins like all the structure you had in the original table. But yeah, it's something to think about, definitely.
All right, let's keep going.
Yeah, cool. Are there any downsides of zkSummit on Ethereum versus standalone chain like Zcash? It's a good question. There are some pros and cons. The downsides would be you have to play by the rules of the blockchain you're working on. We have to use at the moment BN254 as our time-friendly elliptic curve because implementing any other kind of elliptic curve without pre-compile support would be hideously expensive. Whereas obviously if you're running your own chain, then you can implement whatever you want. You also, because you're obviously sharing a blockchain with everybody else in the world, the cost of data can become a bottleneck. For example, if you with the zkSummit rollup, if you want to do data availability on chain, then there's a cost to that, which obviously if you're running your own chain, you could probably mitigate that. But the upside is obviously the much larger user base. You don't have to grow the traction of your own chain. You don't have to create your own consensus network, which via proof of work right now would be very difficult in the modern world, just unless you use a radically different algorithm that people couldn't use existing like Aztecs or GPUs on. And also, obviously, what we really like about what we're building on Ethereum is we can focus on adding value the way that, like in the best way that we can. We can focus on the cryptography, on the implementation. We don't need to have the overheads of running our own chain. So it's a very mixed bag, I'd say. What is the overhead to include lookup tables in the circuit? The overhead is the prover. Well, if we split things out to prove and verify overheads, the verify overheads are approximately, I think it's going to end up with about 6 or 7 extra elliptic curve scalar multiplications the verify has to do, which is not insignificant. But like relative to the 2 linear pairings that the verifier already has to compute, like the marginal increase in verified complexity is not that large compared to existing PLONK. For the prover, you need to commit to the sorted list of lookups, which is at least one kind of extra polynomial commitment. In the paper, it's 2, but effectively you can leverage the fact that in a PLONK circuit, not every gate is going to contain a lookup, which means that basically you can probably.
Yeah, Zach, I think that's maybe a little too. So I think at a simple level, you need to add to your witness, like this sorted. You need to pay with this sorted witness, where you pay basically the size of the table once, and you pay for each thing you want to check in the table. You pay for another field element. So basically, all these things you want to look up, you need to write them twice, like once in the original witness and once in the sorted witness.
Yeah, the zkSummit rollup construction is going to be very, very heavily. It's going to follow in the footsteps of Zcash, using the concept of nullifiers to break the transaction graph and achieve full privacy. What is Aztec's top open snark research problem? Oh, we have so many. No, sorry. Okay, so the one that I think is the big one for us right now is if you look at the kind of the PLONK, TurboPlonk, UltraPlonk, you look at what the prover is committing to. The majority of the polynomials are committing to the kind of the evaluations of these polynomials on the subgroup multiplicative subgroup we use. Their values basically range across the entire field because there's a lot of randomness injected into them. With UltraPlonk, there's going to be 13 polynomial commitments, and only 4 of those, the evaluations on H of these polynomials will reflect witness values. This is like it's irritating because generally in a snark circuit, a lot of your witnesses are going to be quite small. For example, if you're doing binary Boolean logic, your witness values are going to be 1s, 0s, short integers. And this, if you pre-process your structured reference string, this has a direct correlation with prover time. Because if you're doing scalar multiplication and your scalars are short, that's faster than if your scalar multipliers range across the entire field. And for Plonk, 9 out of the 13 polynomials, the scalar multipliers do range across the entire field. So I guess the open research problem is, can we reduce that somehow? Can we make these commitments either have like lower degree or have values that are more controllable, more directly related to the witnesses? Similarly, I think another open research problem, which maybe these things are combined a bit, is the Fourier transforms that you have to do to construct a Plonk proof are quite relatively large, and so reducing those, the cost of those, the number of them, or the complexity is another big open problem. I don't know if you have any others to add, Ariel.
So I think the specific case of range proof, where the lookup table is just 0 to m, I think that can be improved probably significantly from the Plookup paper. So I think that's a great thing for people to think about.
Also, I just want to give you a heads up that I'm actually going to be heading over to the break section, but I want to keep you guys going here. So I know I announced it earlier, but I stuck around, but now I'm actually going to head over there. So keep going if there's more questions, or come join me at the break session shortly.
Cool. So I think that's all the questions on the list answered. If anybody has any other questions, happy to continue. Otherwise, maybe we should jump into the break room.